grade 12 sanibonani sondelani ngapha sizofunda Euclidean geometry. So ake sibone siphiwe ini. In the diagram, a circle passes through BD and E. Diameter ED of a circle is produced to C, and AC is a tangent to the circle at B. So here there are two keywords in that sentence. So there is a diameter. Remember, diameter subtends 90 degrees. So an angle that is opposite to diameter is always 90 degrees. And then we are given the tangent. So remember, there are two theorems under tangent. Tangent is perpendicular to radius at the point of contact, also tan-cot theorem. We are told that AM is perpendicular to DE. So these two angles here, they are equal to 90. They are equal to 90 degrees. Now, the first question here, we are required to prove that FBDM is a cyclic quad. So there are three ways we can prove a cyclic quad. We can use converse angles in the same segment. We can use converse opposite angles of a cyclic quad. We can use converse exterior angle of a cyclic quad. Now, we can see that angle M2 is equal to 90 degrees. So that one is given. We can also see that angle B2 is opposite to our diameter. So it is equal to 90 degrees because diameter will always subtend 90 degrees. Now, this one we can just say angle in a semicircle, and then therefore F, B, D, M is a cyclic quad. Why is it a cyclic quad? It is converse exterior angle of a cyclic quad. So this angle here is 90, this one is also 90. So exterior angle of a quad is equal to opposite interior. So therefore we have a cyclic quad, even though the circle is not drawn, so we know there is a circle outside there. So going forward, we are going to use it as a cyclic quad. Question number 2. Prove that B3 is equal to F1. If I'm proving angles, I will check every angle that is equal to B3. I will also check every angle that is equal to F1. Now, let's check B3. Now, remember, we are told from the statement, this line is a tangent. So now here is an angle between the tangent and the chord. If we use E as a chord, so that means B3 is equal to, which angle is opposite to BE? It is D2. So B3 is equal to D2. That is tan-cot theorem. That is tan-cot theorem. Okay, so these two are equal. But also, remember, we have proved that this is a cyclic quad. So F1 is equal to D2. So also angle F1 is equal to D2. That is exterior angle of a cyclic quad. So now we can then conclude and say, therefore, B3 is equal to what? Is equal to F1 because they are both equal to D2. Okay. Question number 3. 10.1.3. 10.1.3. Now we are required to prove that triangle CDB CDB and and triangle CBE are similar. So now let's go to the diagram and check the triangles in question. So we have triangle CDB. Here is triangle CDB. So basically here they are talking about the entire C. They are talking about D1. They are talking about B1. And triangle CBE, they are talking about, where is CBE? This yellow triangle here. So they are talking about C, the entire C. They are talking about B1 and B2, 1 and 2. They are talking about the entire E. Now, since the triangles are given, angle C must be equal to angle C. Angle D1 must be equal to angle B1 plus B2. And then angle B1 must be equal to angle E, in that order. So now let's check. We can see that angle C is equal to angle C. It is a common angle. This is a common angle. And then now we need one pair. Remember here, when you are proving that two triangles are similar, you just need two pairs of angles that are equal. And then the third one will be equal automatically, because in a triangle, once if you have two triangles, once you have two angles that are equal, the third one will be also equal because of sum of angles in a triangle. So B1, we can see that B1, here is B1. B1 is an angle between the tangent and the chord. Remember, this is the tangent. If we use our DB as a chord, so we'll get our angle B1. And the angle that is opposite to the chord is E. So B1 is equal to E. Why? This is a tan chord theorem. Okay? And then now we have two pairs of angles that are equal. And then the third one is also equal. So we can then conclude from this and say the third one will be D1 is equal to B1 plus B2. I can just call it CBE. CBE. This is a third angle of a triangle, or sum of angles in a triangle. We can conclude and say, therefore, triangle CDB is similar to triangle CBE. Why are they similar? Because of angle, angle, angle. Now, after you have proved that triangles are similar, you please indicate the sides that are in proportion. So, for example, CD over CB is always equal to DB over BE, which is equal to CB over CE. Okay, let's move to the next question. So if it is further given that, so we need a diagram with this one. Okay, let me erase here. Okay, let me move this diagram a little bit. I can move it. So if it is further given that CD is equal to 2, so you just put 2 where there is CD, and DE is equal to 6, so the entire DE is 6. Calculate the length of BC. Now let's check BC. If we do have a BC, here is BC, and we are given our CD as 2, And then we do have our CE. Remember, CE, when you combine CG and DE, we are going to get CE as 8. Now, we can say CD over CB is equal to CB over CE. Why? It is from similar triangles. So now, what is our CD? From the diagram, our CD is 2 over CB. This is equal to CB that we are looking for over what is our CE? It is a combination of CD and DE. So it will be 8. Cross multiply, we are going to have a CB squared is equal to 16, and then put a square root on both sides, so our CB is equal to 4. Remember, we are talking about the length here, so the answer is positive. Remember, the square root is plus or minus, but because we are talking about the length, so our answer is positive. So let's move to the last question. Let me write my CB first in the diagram. So our CB is equal to 4. CB or BC is equal to 4. This one here is equal to 4 units. Okay, calculate the length of BD. Let's check where is BD. So now we have this one. We have that one. We calculated. We need this one. Okay, let's see. So last question, we are going to say CD over CB is equal to DB over BE. Again, it is coming from similar triangles. Now we do have our CD as 2 units over, we calculated our CB as 4. This is equal to DB over BE. Okay, now we can have 1 over 4 is equal, not 1 over 4. If we simplify this, it would be 1 over 2. 1 over 2 is equal to DB over DE. And then we can write this as 2DB. 2DB is equal to DE. So DE, let me go back to the diagram. So DE, ufana no 2BD. Where is DE? DE, we do have DE as 6. Why am I having... Oh, there's... Okay, here it's not DE. It's supposed to be BE. Let's fix this one. So this one is BE. Even this one here, it will be BE. Not DE, but BE. So BE is the same as 2BD. This length here can be written as 2. It can be written as 2 dB. And remember, we want to calculate this BD. Now, if you look at this triangle, remember we said here we have 90 degrees. Here is another BD. We can use Pythagoras theorem to calculate BD. So now let me erase here for the space. So to calculate BD that we are looking for, we can now say DE squared, the square of the hypotenuse, DE squared is equal to BD squared, BD squared, plus this side squared. So it is plus BE squared. That is a Pythagoras theorem. So we are going to have 6 squared is equal to BD squared that we are looking for, plus, instead of this BE, I'll put 2DB squared. Now, this is 6 squared. Okay, 6 squared is the same as 36. Is equal to, this one will give me, this one will be 4DB squared plus 1. So it will be 5DB squared. Okay, divide by 5 on both sides. So we have 36 over 5 is equal to DB squared. And then we put a square root on both sides. So DB that we are looking for will be 6. Square root of 36 is 6 over 5 is not a perfect square, so it will remain under the square root. So it will be 6 over root 5. And then we are done with this question.